Okay, welcome back everyone. In this video, we're going to continue our discussion of momentum by looking at conservation of momentum and types of collisions. So what we're trying to figure out in this segment is when is momentum conserved, so what conditions are necessary, and how are elastic and inelastic collisions different, and how do we analyze them? So first, we're going to begin with when momentum is conserved. So we say that the linear momentum of a system is conserved unless the system experiences an external force. And just to go back to that, that's because of what we said previously, that the external force is equal to a change in momentum over a change in time. And so this is what we talked about in the last video, where we took Newton's second law and rearranged it in terms of force and momentum. And we also wrote this as F delta T equals delta P, where F delta T was the impulse and delta P was the change in momentum. So you can see that if the external force acting on a system is zero, then delta P must also be zero. Now delta always means final minus initial. So this means that the initial momentum of the system must equal the final momentum of the system. And this is something that we can apply to many different situations. So let's talk about the specifics of this. First of all, in all collisions, momentum is conserved as long as we neglect friction and other external forces during the collision. And most of the time, this is not going to be a problem. But if you have two things that are slowly colliding on a rough surface, then maybe friction is slowing them down as they're colliding. But typically, we say that momentum is conserved because even if I have objects A and B that are colliding because they're moving towards each other, they're going to be exerting forces. There's going to be a force of A on B, and there'll also be a force of B on A. And this is Newton's third law. These are equal and opposite forces. But if I isolate the entire system, they cancel out, and the external or the net force on the system is zero. So this is how we can say that in all collisions, momentum is conserved. Now in elastic collisions, there's no deformation of the objects, okay? And that means that kinetic energy is also conserved. So the change in kinetic is also equal to zero, which means that kinetic initial is equal to kinetic final. So elastic collisions have momentum initial equal to momentum final, and they also have kinetic initial equals kinetic final. So we have two equations, and that really helps us because oftentimes we have two unknowns for elastic collisions. And we'll see an example of that in a few moments. In elastic collisions, you have deformation and kinetic energy is lost. Okay, so the change in kinetic energy is not equal to zero, and there's actually three things that can happen when you lose kinetic energy. Well, sorry, two things can happen. You can either gain kinetic energy, or you can lose it, or it's not changed at all. So I guess that's the third. Okay, so in a perfectly inelastic collision, this is where objects stick together and kinetic energy is lost. So K final is typically less than K initial. And this isn't something you have to memorize, just to think about it. An explosion is the opposite of this, and kinetic energy is gained. So another kind of energy, perhaps some sort of potential energy in a stored form, is turning into kinetic energy. So kinetic final is somehow greater than kinetic initial. Okay, so now let's look at some examples. First of all, here's a 1D problem where we have a 1.5 kilogram cart traveling at 1.5 meters per second. So we'll call that M1 and V1 initial. And it collides with a stationary 0.5 kilogram cart, and we'll say V2 initial is 0 and M2 is 0.5. And it's going to stick to it. So we want to know at what speed are the carts moving after the collision. So I'm kind of demonstrating a problem-solving technique here, is that we draw and label pictures of before and after so that we can apply conservation of momentum to it. And so for this, we have a perfectly inelastic collision where they are sticking together. So kinetic energy will change, but momentum initial, and this is just a really long equal sign, is equal to momentum final. Okay, so that means that M1 V1 initial plus M2 V2 initial is going to be equal to M1 plus M2 times V final. Now, why did I add M1 plus M2? Because they are stuck together, and therefore they're traveling at the same speed, and that's what we want, that VF. Okay, so it's just 1.5 kilograms, 1.5 meters per second, plus 0.5 times 0 is equal to 2 kilograms times V final. So it's often useful to write this out, even if you don't think you have to, just to kind of think about what's going on. So that's gone. That's going to be 2.25 kilogram meters per second is equal to 2 kilograms times VF. And I'm leaving in units to show you that it cancels out correctly. So VF is going to be about 1.125, we'll call it 1.13 meters per second. And that makes sense because if you look at V1 initial, it was going at 1.5, but that had 3/4 the mass of the system. So that kind of had 3/4 of the final momentum. So the final speed should decrease to approximately 3/4 of what you started with. Okay, here's another example. What's the recoil velocity of a 120 kilogram cannon that fires a 30 kilogram cannonball at 320 meters per second? So I'll do a horizontal example. Okay, so the cannonball is 30 kilograms and it's getting fired at 320 meters per second. And the cannon is 120 kilograms and we're looking for its recoil velocity. Now this is actually an explosion, and one characteristic of explosion problems is that the initial momentum of the system is 0. Because if you think about it, okay, well, that's a bad picture, but you have the cannon, you have the cannonball inside of the cannon, and nothing's moving. So P initial is equal to 0, and this is actually a picture of P final over here. So 0 is equal to, and we'll call the cannonball M1 and the cannon M2. So it'll be M1 V1 final plus M2 V2 final. Okay? Now, one thing you want to keep in mind is don't try to guess a final velocity direction. Just add it up, and if something is going in the negative direction, the math will make that work out. So in this example, we have 30 kilograms for the cannonball and 320 meters per second, okay, plus 120 kilograms for the cannon and V2 final for the cannon. Okay, so I'm going to evaluate that. 30 times 320 is 9,600 plus 120 kilograms times V2 final. Okay, did I do that right? I think so. So then what we're going to have is negative 9,600 kilogram meters per second is 120 kilograms times V2 final. And kilograms is going to cancel. We divide by 120. And I think that's going to give us just about 80. Can't do math this morning. Yeah, so that's going to be V2 final is equal to negative 80 meters per second. Now, one thing that we can notice here is that V2 final is negative 1/4 of V1 final, and that's because M2 is equal to 4 times M1. So in order for the momentum to cancel out, the cannon has to have 1/4 the speed because it has 4 times the mass as the cannonball. Okay, so hopefully that makes sense. Okay, so now we have two blocks that are 0.5 kilograms and 1.5 kilograms, and they're placed on a horizontal frictionless surface. A light spring is compressed between them, and a cord initially holding the blocks together is burned. Ooh. So after this, the block of mass 1.5 kilograms moves to the right with the speed of 2 meters per second, and we want to know what's the speed and direction of the other block. So we want V2 final, and then we also want to calculate how much elastic energy was stored in the spring. So this is another example of an explosion problem, and it's similar to the last one with the cannon, where we have basically initial momentum is equal to 0, and so that has to be equal to final momentum. So 0 is equal to 1.5 times 2 plus 0.5 times V2 final. So negative 3 kilogram meters per second is 0.5 kilograms times V2 final. And we're going to get V2 final is equal to 6 meters per second, the negative sign. And again, this is the same idea. Because we have 1/3 the mass, we have to have 3 times the velocity. But now, what was the original elastic energy in the spring? Well, we could write that as 1/2 kx squared, but we don't know k and we don't know x. But that is the elastic spring energy. And what happened to that spring energy? It went into the blocks in the form of kinetic. So M1 V1 final squared plus 1/2 M2 V2 final squared. So we just plug it in. M1 is 1.5, V1 is 2, and then 1/2 times 0.5 and negative 6, which isn't going to matter because it's getting squared. Okay, so that's going to be 4, a half of that is 2 times 1.5 is 3, plus 36 times 1/4 is 9. So there were 12 joules of elastic energy in the spring. Okay, we're going to do one more example, and this time we're going to do an elastic collision, and then we're going to do two-dimensional. Okay, so we'll finish up this lecture with a 1D elastic example, and then we'll move on to 2D. Okay, so now we have the same 1.5 kilogram cart moving at 1.5 meters per second, and it's going to collide elastically with a 0.5 kilogram stationary cart, and we want to know at what speeds are each of the carts moving after the collision. So this is different now because we have two variables, V1 final and V2 final, and this means that we're going to need to have two equations with two unknowns. So we could make a guess as to which way these are moving, but like I said, the math is going to dictate what's happening, so we don't really need to worry too much. If I was going to guess, I would guess that both of them are probably going to keep moving to the right because the 1.5 kilogram has more mass, so it's got a good deal of momentum compared to the 0.5. Now, if the 0.5 was originally moving to the left with a lot of momentum, that would be a different story. Okay, so we're going to set up two equations. First of all, momentum initial equals momentum final. So this means that 1.5 times 1.5 plus 0.5 times 0 is equal to 1.5 V1 final plus 0.5 V2 final. Okay? And so what you notice is that I haven't guessed any directions for these. I'm just putting them in as V1 final and V2 final. Okay? So it's 2.25 is equal to 1.5 V1 final plus 0.5 V2 final. Now let's just rewrite that, multiply by 2. So 4.5 is 3 V1F plus V2F. Or in other words, V2F is 4.5 minus 3V1F. Okay, remember that. We'll come back to that. Now, we're going to set up kinetic energy. Kinetic energy initial is equal to kinetic energy final. So, this means that 1/2, 1.5, 1.5 squared, plus 1/2, 0.5 times 0 squared, so that's still gone, is equal to 1/2, 1.5 V1 final squared, plus 1/2, 0.5 V2 final squared. Okay, so now we have some somewhat nasty algebra to do. Okay, so 1.5 squared is 2.25 times 1.5 again times 0.5 is going to be 1.6875. But here's a little trick. I can get rid of all these 1/2s and I can multiply everything by 2. Okay, so that's really going to be 3. Whoops. That'll be 3 and that'll go away. So 1.5 squared times 3 is just going to be 6.75, and that's going to be equal to 3 V1 final squared plus V2 final squared. Okay, so you might notice at this point that we still have two variables and we have two equations. So we're going to take V2 final and actually plug it in right here. So that's going to be 3 V1 final squared plus the quantity 4.5 minus 3 V1 final squared. Let's evaluate that. So on one side we have 6.75. On the other side we have 3 V1 final squared. And then 4.5 squared is going to be 20.25. And then we're going to have 4.5 times 3 times 2. We'll have 27 V1 final. That's my sort of two middle terms. And then I'm going to have plus 9 V1 final squared. Okay, so now we're going to collect our terms and we're going to have basically 12 V1 final squared minus 27 V1 final, and then 20.25 minus 6.75 is going to give us plus 13.5. And sorry about that. It's 27 and V2 final. Or sorry, that's V1 final. Lots of places to go wrong with elastic collisions, right? And that is going to be equal to 0. So now we need to use the quadratic formula. So V1 final is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. And I'm going to hope and pray that that's going to give me a positive number, or else that means I did something wrong in my algebra. Okay, and lo and behold, this is actually going to work out really nice because everything under the square root is just 81. So we're going to have 27 plus or minus the square root of 81 over 24. So it's 27 plus or minus 9 over 24. And this is going to give us, let's see, it's going to be 18 over 24ths, or it's going to be 36 over 24. So that means we get 0.75 or 1.5. Now I want to point something out to you. I know that I did this math right, and the reason is that one of the answers that I'm going to get for V1 final is actually going to be V1 initial. So that's not the actual answer because that's what we had up here. V1 initial is 1.5. So that tells me that V1 final is actually going to be 0.75. So the quadratic equation has two solutions, and one of the solutions is like the collision never happened. Okay, so we can then take this and plop it into here to solve for V2 final. And notice, by the way, that 4.5 minus 3 times 1.5 gives us 0, which was V2 initial. Okay, but if we plug in 0.75, then that's going to give us V2 final is 2.25. Okay? Now, there's one more thing that I want to show you that's extremely important about elastic collisions. And I know this video is running a little bit long, but this is really important. So, here's the cool thing about an elastic collision. If you take V2 initial and subtract V1 initial, you're going to get the opposite of V2 final minus V1 final. And this is a well-known fact about elastic collisions, that the relative velocity just flips. Okay, and this is because the kinetic energy is conserved. And I'm not going to go through the proof right now, but the fact that the kinetic energy is conserved means that you can sort of flip the relative velocity. So V2i is 0 and V1i is 1.5, so that's negative 1.5 on one side. We put a negative sign, and 2.25 minus 0.75 is 1.5. So that does indeed check out. Okay, so this video is already way too long, so I'm going to stop now, and in the next video we're going to talk about two-dimensional collisions.